JBO, otherwise known as Jonathan Barr Orr, is presenting Breaking Secure Boot, Exploiting Grub2's Forgotten Attack Surface and Other Bootloaders. That's a hot topic if you've been following the media lately. People are finding all kinds of ways to get around bootloaders, and Jonathan is exceptional at it. Jonathan Barr Orr is an information security expert and a hacker focusing on binary analysis, vulnerability research, application security, reverse engineering, and cryptography. His research has uncovered critical vulnerabilities that have impacted millions of users worldwide, shaping security best practices across the industry. Frequently cited by major news outlets, his work has influenced both academia and industry, driving meaningful security improvements. He is also a seasoned public speaker, which he has been at almost every one of our events, has been a presenter. His presentations have always been excellent. He is presenting at top security conferences and sharing deep technical insights on exploitation techniques, mitigations, and emerging threats. So without any further ado, I'd like to welcome JBO to the stage.
Thank you. I appreciate it. So let's get started. This is, the title was longer, but I call it Kickstarting Bootloader Vulnerabilities. I'm very, very happy to be here today to talk about my research. So without further ado, a bit about who I am. I was already introduced, basically. Some minor details is that I work currently at Microsoft as a security research architect. And interestingly enough, even though it's Microsoft, I do work that goes beyond Windows, and that includes all major operating systems and beyond. I like finding interesting bugs, and most of my publications you can find on my website. Now, interestingly enough, I do not see the slides moving. Can you guys see the slides moving? I see it only on the top left corner, but I don't see it in the actual space.
No, I see it on the top left corner, but the one on the main screen isn't changing. Try restarting the slides and see what happens.
Let me try. Yeah, let me retry. I apologize.
No, this is we're hackers. We improvise, adapt, and overcome. Not a problem. I've seen a problem. This isn't it.
Retry one more time. Share my entire screen this time.
Technology's hard.
Okay, this looks better.
Yes,
it is hard. So this is a bit about me and my personal website. I try to keep like most of what I think, I guess, there. Well, not most, but some. A bit about the good old days. In the good old days, if you're old like me, then you used to use BIOS a lot. And what happened really is that when you boot up your computer, your BIOS loaded from boot ROM and runs something called toast. Interestingly enough, it runs on Intel machines. I'm only talking about Intel. It ran in real mode, which is 16-bit 16-bit mode with segmentation and whatever. It was really fun times, but we won't be touching on that too much. Some of the things that BIOS does besides, that post check and make sure that like initialization of memory and stuff like that is register useful interrupts in something called the interrupt vector table, or IVT for short. And then based on the boot order, it would locate something called an MBR, that's the master boot record, and would load it. Bootloader first stage would be loaded at like 00007 C00. That's the address. And it would basically be read from like first sector of the disk, which is 512 bytes. And then that bootloader like can do whatever, but it will typically use interrupt number 13 to read chunks of the disk to load a second stage. This is how basically bootloaders work, or used to work at least. And eventually bootloader will load a kernel from the file system, and the kernel will continue loading your operating system. So with that, what seems to be the problem? Like what was wrong with the BIOS world? And then one of the issues that was interesting is that there was no standardization for BIOS. There were many companies this is a screenshot of how BIOS might look like or used to look like. And one I don't know, something funny that I remember is that if you ever debug the BIOS or wanted to debug a BIOS, you'd notice that a lot, like you'd have to debug by ear. Like the BIOS, upon failure, it would actually beep, and based on the number of beeps, you could actually know what the issue was. So we're talking about like very raw stuff, and that's understandable because the BIOS wouldn't be able to initialize like, the monitor or keyboard or whatever. So you had to rely on very, very crude methodologies. And back in the day, it used to be a lot of fun, and there was a lot of like BIOS hacking and modding communities out there. So the problems is that there is no standardization. BIOS updates, by the way, were done with proprietary software. Interestingly enough, okay, BIOS updates, there was no standardization. BIOS updates were done with proprietary software, and bootloaders are kind of like problematic because there is no verification of the MBR by the firmware, right? BIOS basically loads like 512 bytes and basically runs them. There's no verification of the firmware itself in many cases. So if someone modded their BIOS and with like malicious code, it would basically run. And bootloaders, that basically gave rise to bootloaders, to bootkits, I mean. You could basically either override the MBR, you could, if you were clever, you could override the firmware, the BIOS code, and commonly you could also hook interrupt number 13 via the IVT modifications that I mentioned, and basically be kind of like a man in the middle between, let's say, the bootloader and the disk, right? And you could modify it any way you wanted. And besides that, like one other problem is that BIOS code used to be buggy or vulnerable. And again, I don't see updates. Amazing. I'll try to. Okay, this looks good. And this is if you ever wanted to know how to work, like how BIOS works and what have you. This is the personal recommendation that I have for a book about it. So how do bootkits used to work? Infect the MBR, that's like the traditional way, and then hook several interrupt vector table like entries, and then load the OS. Commonly, interrupt number 13 used to be used for infection for disk reads and writes. Interrupt number 15 is called the system interrupt, and you could inject malicious code or modify BIOS memory. And then there was interrupt 1A, which was the clock interrupt that basically you could do a countdown and only introduce your code at a later stage. So all of these were valid ways of creating bootkits. And we're in 2025 now, so we have UFI. UFI is not new, but and it's not unified, unlike the name, but it's supposed to be unified. So it's called the Unified Extensible Firmware Interface, and it's supposed to be a replacement for BIOS and kind of like a standardization of services and modularization of everything. And then more importantly, there is a root of trust. There's something called a platform key, which is like a baked-in key that's baked into like the hardware. That derives, this is all in a nutshell. I won't be going into the nitty-gritty details, but that derives something called key exchange key, which signs two types of databases, which is called DB and DBX. The DB is basically a set of hashes of bootloaders that are allowed to be run, and the DBX is the ones that are revoked. So that's kind of good. That's kind of great, and basically, like one of the main features that uses UFI or part of UFI is secure boot, which basically means that everything is kind of validated. The platform key, which is baked in, it validates like the key exchange key. The key exchange key validates DB and DBX and so on. And now I realize that I will probably have to do it every single time, which is not fun, but it is what it is. When I say it, I mean the screen sharing part. I don't know if I'm the only one that sees this, but apparently I'll have to do it every time.
Yeah, we
wish I
haven't
would
seen.
automate this.
Very odd.
Yeah, yeah. When we first tested, that was not that way. So I don't know why that happened, but okay. Conceptually, this is what you need to remember. There is a platform key that points at the key exchange key, and then the KEK points to DB or DBX, and then Eufy basically would load only entries from DB, but not from DBX. This is how it looks like. And just to put it out there, Eufy still has major issues. There are entire companies that tackle those things. Binarly is a well-known one, and huge respect for them. And there is one more report that I found interesting from this year, from January, that talked about one of the modules inside Eufy by some OEM that was signed and basically what could be used to load arbitrary files without signature verification, which kind of breaks entire secure boot, breaks the entire point. So Eufy still has issues, but it's like infinity times better than what we used to have in the old BIOS days. Now I want to talk about Grub2. And again, the screen doesn't load well. So I'll do that for every transition. I know that it sucks, but you guys will bear with me.
Well,
and we'll do fine.
The screen doesn't change, but the little window that we can click on in the top left and bring it full screen, that is changing for some reason. The main screen.
Yeah, so you'll have to tell me like, yeah, so okay, I won't be changing those, and I would say that my recommendation would be looking at the top left part. I don't know how the recording looks like. I'll have to check that, or if you could check that for me, that I would really appreciate.
Yeah, the recording is showing the zoomed in screen, so you're fine.
Okay. Okay, let me just continue, and hopefully everyone looks at the top left part. I appreciate it. So Grub2 is a bootloader, and it's mostly used for Linux, and it's fully open sourced. It supports many interesting file systems, just like Linux does. It has really complex features, like there are fonts, there is networking, there is backgrounds. You can do a bunch of stuff just with Grub2, and it's compatible with multiple architectures, MIPS, ARM, obviously Intel. And because it's open sourced, it poses kind of a challenge when it comes to secure boot, because open source digital signatures don't usually go hand in hand sometimes, especially if you wanted to tweak your own like Grub. And what really happens is that OEMs have a small approved shims. Those are like tiny programs that basically load Grub after verifying it. So that's the way that loading works. And you can get like really crazy stuff if you customize your Grub. For instance, this is an actual like screenshot of someone that customized Grub to basically look like the Doom like selection screen, which is really cool. A mental picture of everything. So we have the platform key, which derives the key exchange key, which would load only entries from DB but not DBX. And then basically based on that verification, we'll have one of those like OEM shims that I just discussed. Shims would verify and only then load Grub2, and Grub2 would load the operating system, Linux most commonly. Let's continue. What's wrong with Grub2? There is something that Google released, Google Chromium, that I really like, and it's called the rule of two. And the idea is that you cannot have, you can only choose two out of those three boxes that you can see, or three circles. One of them is that code which processes untrustworthy inputs. Think about Grub for a second and the amount of file systems and like media and graphics that it does, networking. There is code that's written in unsafe language, C or C++. Grub2 is like entirely coded in C with some assembly, which is also not a safe language. And then code which runs with no sandbox, like for instance, a browser process without a sandbox is kind of like a problem. Obviously, Grub2 does not have any sandbox to run. It just basically runs on like almost bare metal. So like basically all bootloaders, or most bootloaders these days, fall under this like Doom category, which we're going to exploit. As I mentioned, there's no sandbox, and since there is no OS, there's no ASLR, no DEP, no type of memory protection at all, no stack cookies, because what would you do if you like hit a stack cookie? It handles, as I mentioned, large untrusted inputs like file systems, graphics, networks, and so on. It's coded in C, and like obviously C is the programming language to do something like coding a bootloader. And I did find some interesting Rust bootloaders. None of them are actually trusted by Secure Boot without adding specific keys manually to the DB. So they're not standardized at all. And for all means and purposes, Grub2 is the standard for Linux. So, so just an FYI. Some examples of things that that were found in the past. I usually like to look at the past before I start my own research. So there are a few interesting vulnerabilities. I will not go into each and every one of them, but some of them are like really like easy stack-based buffer overflows. Like the first one with the config file basically being into a constant buffer. There are multiple like image parsing vulnerabilities, multiple network vulnerabilities. One of them was a shim vulnerability, which was interesting, and one of them was related to file system, MPFS specifically, for a heap out of bounds. All of them are really cool and worth checking out. Now, I had time, this was December 2024 when I started that research, and December is great because there are no meetings if you work, especially if you work in a big corporate, or very little meetings. Everyone goes on vacation, and that's great for me because December for me means research time. That's basically what I'm trying to say here. And I usually like to use a few approaches when looking into something. Fuzzing is a favorite of mine, and I started doing fuzzing for the video and graphics of Grub2. And if you think about it, it's extremely hard to fuzz bootloaders because, well, they're bootloaders. But luckily, there is something called GrubEmu, which comes with Grub actually, and it's an emulator of Grub. It's not perfect, of course, but it's still an emulator. And I had to like do some minor code modifications to the Grub source code to be able to run with AFL++. It was very, 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 very slow, but I gave it a shot. And my favorite approach is running a fuzzer in the background while I actually look at the code like with my own eyes. This is how it looks like. This is a recorded demo, and if you could see like that little screen actually popping and like going on and off, it's because I test like the graphics library. So you'd see like every like few times a second, you'd see that it actually pops on and off, and this is every time it's like a run. And the graphics were really interesting because they support like parsing of JPEGs, for instance, right, and so on. So with that, let me move to the next slide. With that, one of the things that while that thing was running, I was looking at stuff that were harder to fuzz, aka the file systems. And I started looking at the file system implementations, and I was working a bit with Copilot and some other tools. That's actually pretty interesting. I think that's the first time I used an LLM to help me with analyzing the code. And my conclusion, by the way, is that like it's not always right. It's not bullet. It's not like a silver bullet, but Copilot definitely helped me here and saved me like a week worth of work, which is pretty good actually, especially if you're lazy like me. And it still has a lot of false positives, but it was able to point out some points in the code that were like more sensitive than others or coded in a weird way. And you discovered that many unsafe operations. And one of the issues that I had is trying to conclude exactly what is attacker controlled. Copilot was not very good with that. And Copilot was not very good also with dependencies between different modules. So that's another thing to take into consideration. And I managed to automate my process a bit with the help of Copilot as well. So basically, the LLM pointed out many issues. Roughly 67% were false positives. The rest were real issues, being in severity. LLM was not good at pointing out exploitability chances. LLM had misses for certain things, and LLM was not bad creating boilerplate exploit code, which was really nice. And it was fantastic at covering complex code QL queries. If you'd used code QL, then basically, like, apparently Copilot is amazing at writing code QL, which is kind of complex in my case. So that was good. And as I said, it saved me roughly a week. As a reminder, I hope that you guys are looking at the top left, like this Zoom part of the screen, just to make sure, because there is a synchronization issue when I'm presenting in this VR space. So this is an example of a bug that that I found with the help of Copilot. And basically, this bug is a parsing of symbolic links in a file system called JFS. You don't need to worry about how JFS actually is parsed. Like, only this function is important. So I'll point out a few interesting things. First of all, everything that is read from data is actually attacker controlled. So there is grub size T, which is 64-bit unsigned integer, which is basically read from disk. And then that size we allocate with grub malloc, which is not an actual malloc. We allocate that size +1 because the +1 is for a null terminator. If you've ever done strings in C, that should not be foreign to you. And then that would be like the symlink kind of buffer where we save the symlink data. And then basically we read the symbolic link data to that buffer. That's basically what happens here. And lastly, we also add a null terminator at the end, but I won't talk about it too much because it doesn't really matter. So these three issues are actually a bug. Why is that a bug? Well, the size that we read, which is like 64 bits, is read from the user. So size +1 could actually cause an integer overflow. If you're unfamiliar with the concept, an integer overflow is when you have, let's say, 64-bit integer, and you add a number to it. If the number exceeds 64-bit like size, if it exceeds to, let's say, a 65-bit size, then there's going to be like a wraparound. So you can get like weird things, like, for instance, if you had an 8-bit, if you had bytes and you added 1 to 255, you wouldn't get 256, you'd get 0, which is basically what an integer overflow is. So the same thing goes here. You have that size, which is 64 bits. If you do size +1, and then basically it could be 0. And then grab malloc of 0 actually works. It returns a chunk. And that chunk is basically like that symlink buffer is going to have like a 0 size. And basically then we write to it. If you remember, this is what happens with grub JFS read file. So that's pretty interesting because it means that now as an attacker, if I create like that JFS file system and mount it via grub, then basically it's going to parse that symbolic link. That symbolic link will have a size of FFFFFFFFFFF, which is basically like -1. You can think of it as -1. When adding 1, that symlink buffer is going to get like an actual like new buffer from that chunk of a size 0, and then we write to that size 0 like an arbitrary, like really large number of bytes, which we can do with partial writes. So that's kind of like a description of the bug. And I discovered similar issues across all different file systems and some new ones. All of those are parsed by grub2. Interestingly, by the way, all of the code that parses those file systems does not come in like a form of a driver or something. Again, this is a grub2. It runs like on like the actual hardware of the machine. It doesn't have any drivers to call to. So all of the code there is kind of like copy pasted, and some of it is in great quality, some of it is not in great quality, and you can read the set of like issues that I found. Besides that, I found like 2 other issues which are related to like the ability to read arbitrary data, but I won't be discussing that here for now. Most of those issues, like the vast majority of those issues are issues with just memory corruption vulnerabilities. The grub2 heap, the one that basically returns like grub malloc call, is very simplistic. It's reminiscent of DL malloc if you're familiar with like any heap implementation. Grub2 is single-threaded, so that makes sense. You don't need like arenas and stuff like that. And it allocates new memory from UFI under the hood in something called regions. And it basically uses a very simple metadata structure before the return chunk. So the metadata contains the next free block pointer, the current block size, some magic, which basically says either you're free or occupied, and some padding for memory alignment purposes, because you want them to be memory aligned because it's faster. And I didn't need to perform any complex heap shaping. I discovered that allocations exist in a very predictable locations in memory, because again, there is not a lot of randomization when you boot up a machine. And I could do heap shaping because I control the file system. So if I needed to, I could arbitrarily make grub allocate more data if I wanted to. And I found a function pointer in offset 130 hexabytes after the allocated chunk. And that function pointer is all I needed, because that function pointer is going to be called. And interestingly enough, if you look at grub implementation, you'll see that all file system implementations have function pointers for operations. Kind of reminded me of C++ vtables, but the idea is the same. So for instance, for NTFS, as you can see here in the example, you can see that we have like a function pointer for directory listing, for opening files, for reading files, for closing files, and so on. So I basically went for like overriding the close files in each of those like issues that I found, and I was able to get like arbitrary code execution. Again, keep in mind that all pages are like there are no page protections here. Like everything is like super duper easy for exploitation purposes. So I really like that. The exploitation itself, super simple. Cause an integer overflow in a file system, override the close functionality, function pointer, do an obsled to my code. Everything is read, write, execute. So it's just like the 90s, super fun. And I could even find like the UFI services pointer. And basically I wrote my own bootloader. Here is a recording of that, how that might look like. I initially coded power grub. And here, what I basically show is that, secure boot is enabled. I call my Python function, which will basically create the file system mounted, like make grub like automatically mount it. Now I reboot. And here the video didn't do well, but if you can see, basically it's booting, you can see the shim. And then what happens here is that this is my bootloader now. Even though secure boot is on, I was able to load before the operating system and basically created my own like little bootkit, which is not really a bootkit. Just draws a picture and hangs forever. So that was a pretty cool experience. Now, when I finished my research, of course, I reported everything to like grub maintainers and even helped them fix. But interestingly enough, grub is not the only bootloader that implements many of those file systems. As I mentioned, the file systems there actually are kind of like in a bad shape, some of them in terms of coding. And I would call also that they're like minimally functioning. You don't need like fancy journaling or whatever in a file system implementation because you only need to like read files and boot and stuff like that. So interestingly, I discovered that a lot of the because it's open source, apparently some of this code was copy pasted. I don't know if grub was the source and then other people copied from it, or vice versa, or maybe little chunks were copied from grub and some of it were copied to grub. But basically, there is a lot of copy paste between all of those like file system implementations, JFS, HFS, and TFS, all of those things. If you look at open source projects, they basically all look kind of very similar. So I was wondering if all the issues that I found could affect other bootloaders, right? Or other file system implementations that are somewhere on GitHub, basically. Again, I used an LLM to find similar code across all of GitHub. I had to do some work to basically kind of, connect like my Git API with the LLM, but it kind of worked. And I found two other bootloaders that were really popular. One of them is called Bearbox. The other one is U-Boot. And if you're familiar with embedded like coding, then both of them are very popular for embedded scenarios. Think about like IoT and stuff like that. So I got more vulnerabilities on all of them. And like, again, the vulnerabilities are almost identical. Like there is a buffer overflow that comes from the heap based on an integer overflow because something is attacker controlled. I didn't even, like, that was all static analysis. I didn't have like a machine to actually run U-boot and Bearbox. I basically reported those and hoped for the best. And they did acknowledge everything and fixed everything. So that was pretty good. Some disclosure and fixes. I disclosed that to Grub 2 maintainers. I worked with them to fix the bugs, contributed some code myself as well. And most OEMs by this point, again, this was like the disclosure itself happened around January, February, have updated their DB and DBX. There is another mechanism that I won't go into that basically kind of implements like a DBX but in software, which does not achieve much. And Bearbox and U-boot vulnerabilities are fixed. But I would still expect to see vulnerable and patched firmware because unlike Grub, which runs on like computers, U-boot and Bearbox might be just baked into the firmware of whatever IoT devices that you might have. So I would still expect to see IoT devices out there that still use the like vulnerable U-boot and Bearbox. But I would say that the risk there is low compared to Grub because those like Bearbox and U-boot devices or devices that use Bearbox and U-boot will most likely not be parsing arbitrary file systems. So the risk is pretty low. If you could do something like that, that could be cool. But it kind of depends on the device and the functionality of the device. Some summary or statistics, 11 CVEs for Grub, 4 CVEs for U-boot, 5 CVEs for Bearbox. And like my summary is that the state of open source security is not in a great shape. There is a lot of copy pasting. And in my opinion, like everyone, there is like a, this are just my 2 cents. So take it with a grain of salt. But my point of view is that there is a promise or an unspoken or sometimes spoken promise that the open source community would be amazing at basically detecting vulnerabilities early on because everything is open sourced. And that's great. But unfortunately, in my opinion, not enough people actually inspect the code despite being open sourced. And that's kind of problematic. One more thing that I didn't add to the summary is, again, the utility of AI. I have healthy amounts of skepticism when it comes to AI. I'm not like a big fan for using it to solve any problem. But if it can save me a week, then great. And my 2 cents here is that you want to use it as a tool, just like you use a car for it, like as a tool. It basically makes you run faster and better, but you still need to know how to drive and where you're going. Otherwise, like it won't help you. So with that, thank you guys so much. I know I finished slightly early. I do not know if we have time for questions, but I will be more than happy to take some if there are any. Thank you so much.
Yes, we have time for questions. We gave you an hour slot, so there's plenty of time. So if anybody has questions for JBO, go ahead and ask them now.